So now let's look at a case where we would have an obstacle that we would like to avoid. So our robot starts from here, and we would like to drive it using MPC to the reference, right? At the same time, we would like to avoid some obstacles in between, right? So it turns out that this adds as a path, another path constraint for the MPC formulation, right? Right. So what we would like to guarantee, or what we would like to maintain to avoid this obstacle, if we assume that our robot is approximated by a circle, and the obstacle is also, like the perimeter of the obstacle is approximated by a circle, so basically we do not want these two circles to intersect, right? So if we give like a radius for each one of them, so we have a radius for the robot RR and a radius for the obstacle RO. These are the two radii for the two things, right? We would like that the Euclidean distance between the centers of the two be greater than, or at least equal, the summation of the two radii, right? Okay. So what is constant here and what's changing? So assume that this obstacle is static. So XO and YO, the X and Y positions for the obstacle, are static, but X and Y, these will be later the predicted states for the robot. So as long as they change, we always want to maintain this inequality, right? If we would like to transfer this inequality to be an inequality with one side as 0, we basically take this R plus RO to the other side of the equation. And if you would like to have this inequality as less than or equal 0, you invert the formula basically, or the inequality, right? Just invert the sign, and this inverts the equality inequality sign, okay? Right. So so we will implement the same thing as is, except that we will add this extra constraint, right? Sounds good. Right. So we will do the implementation. Everything is pretty much the same as previously. Again, from now on later, we're just using multiple shooting because it's good, right? These are the multiple shooting constraints, the equality constraints. And now we will add extra constraints. I could have put this in the same for loop, but I just wanted to highlight that this is something new here, right? So now we have an extra for loop in which we append more constraints to the vector G. So the first part of the vector G, we put all the equality constraints for multiple shooting. Now we are adding extra constraints, and these extra constraints are basically direct implementation of this inequality here, right? So here we have the change in X squared, the change in Y squared, right? Plus the summation of the two radii. I define the diameter, so I'm dividing them just by 2, and I'm taking the square root of that, right? What is it changing here in this for loop, and what's fixed? What's fixed are the obstacle position, X and Y, and what is changing is my prediction of X, right? So here we're guaranteeing this for all the prediction steps. That's important. It's not for one or a sub number of steps. It's for all prediction steps, right? Right? Because we want all the prediction steps of the robot to avoid the obstacle. Okay? You will see this in simulation very clear. Then the rest of the multiple shooting implementation is the same as before. The optimization variables, just remember that they are my states as well as the control actions, right? The options, and here since we added more G's, I mean we added more path constraints, we should also add some margins on these constraints, right? So we would like this term, we already defined this term. So then what are the margins for this term? What is the lower bound to it, and what is its upper bound? So it's upper bounded apparently by 0, and it can take any value below 0, so its lower bound is basically minus infinity. So this is how we define this inequality constraint. In the previous constraints, both we set to 0 because this was an inequality constraint, right? It was not less than or equal, it was just equals to 0. But this one is less than or equal 0, so it's upper bounded by 0, yes, but lower bounded by any negative number, right? Okay, everything here is the same as before. Then our simulation loop, pretty much the same as before. So let's just look at how this works in Matlab. So I'll go back to Matlab here. So that is yeah, MPC with obstacle avoidance. I will again start with a fairly short prediction horizon, 3 here, right? Then running this and see what will happen. So this was a fairly short prediction horizon. So you see that for all the prediction steps, none of them overlapped with the obstacle circle, right? Again, that's a fairly short prediction horizon. So if we increase it to 10, for example, it should work fine and reach the goal position. Right? So the simulation keeps on because it was long, basically, right? It terminated after the 20 seconds simulation time, right? So if I increase this up to 10, or I think 14 worked fine here. So let's increase this. Well, let's just try 10. So now you'll see more prediction steps. Well, this one, yeah, continue to the end. More prediction steps, and all of them are avoiding the obstacle. All of the steps are avoiding the obstacles, right? Okay, so do you have any question for the obstacle avoidance feature in MPC? Right, so it turned out that obstacle avoidance is just adding more constraints to your optimal control problem, right? Okay, sounds good. All right, so now let's go back to the presentation. Right, and go to the last part of the presentation in which I'll talk about MHE, removing horizon state estimation. So now we're shifting gears, right? So we were doing control, now we're doing state estimation, right? Okay, so let's go ahead and look at what we have in MHE. So MHE is a moving horizon state estimator. That's also known as receding horizon estimation, right? And state estimation in general means that we would like to estimate the internal state of a system from the measurements of the input and output to that system, right? So here we basically would like to do two things. Estimate the internal state of the system, that's one thing. And for that we will use the measurements from the input and output, keeping in mind that these inputs and outputs could be noisy. If they were not noisy and the system was linear, we can use a full state or a full order observer, right? For linear systems, right? And if the system is linear and inputs and outputs are noisy, so that's when the Kalman filter comes in, right? And if the system is non-linear, inputs and outputs are noisy as well, so that's the extended Kalman filter and all of its variants like UKF and particle filter and so on. Well, particle filter is different, but yeah, Kalman EKF and all of its variants, right? Okay, so what do we do in MHE? MHE does the same job, like state estimation, but it's based on optimization, right? So the estimates that it gives are basically it fits the measurements. Like it gets the estimate for the states that fits the measurements that we get from the output, right? And we will see now how we do that, right? All right, so in order to understand what MHE does, let's look at this simple single input, single output system, right? So here I'm adding extra equation for the output, like my sensor, okay? And here I'm also adding the Vx and mu x and mu y, which are noise on the system and noise on the sensor, right? So at a certain time k, I usually would like to estimate the current state at this time step, right? So what we do in MHE is that we look backwards, and for a certain window size of length NMHE, we will look at all the measurements in this window, and all the control actions measurements in this window. So you know what control actions you applied here, right? Right, because you know what control commands you send to your controller, so you know the control actions here. Or you can measure them using the odometer, for example, or right, or a gyroscope or an IMU. You can measure your inputs, okay? And also you can measure your output through the sensor, right? So you look backwards for a certain window size, and you find where your inputs are and where your output measurements are within this window, okay? And then what you do is that you find the trajectory for the input and the best trajectory for the output, for your state that best fit your output and best fit your input. If you look at this one here, here I chose my output y to be exactly my state. So my sensor measures directly my state, right? So the trajectory that fits my measurements here is basically the state trajectory, or the estimate of the state trajectory, okay? This is a very special case just to show you how this graph works. All right. So this is what we do in MHE. So again, we're finding a best trajectory that fits. So these words sounds like we would use optimization again, right? So that's what we do in the end. So we formulate this as an optimization problem. We have a cost function very similar to MPC, cost function, and some constraints that we would like to respect. Okay. All right. So our cost function has basically two terms. The first term is the difference between the measured output and the predicted output, right? And the second term has the difference between the measured input and the predicted input. So this term here might seem not necessary. Sometimes actually you can drop them if you're only interested in estimating the state, just the state X. But sometimes you would like to know what exact control actions went to your robot. So you said that you set the control actions V and omega to be, for example, 0.5 and 0.5. And when you send this to your actual robot, the lower level controller may not apply these values exactly. So this becomes something that you would like to estimate, and you can actually estimate that using MHE, right? So here you're estimating the exact control action that went to the robot, which are not necessarily the control actions or exactly the control actions you send to them, right? Okay. So then that's our objective. I think it's clear. Unless if you have any question, just let me know. I just want to highlight one more thing here. So if you look at the sum for the difference between the output and the predicted output, this sum is one step longer than the sum for the input, right? Because the sum of the this sum for the output, we are interested in measuring this state, which depends only on the previous control, not the current control, right? So this sum will always be greater than the other sum by just one step, right? Okay, so what are the constraints that we would like to respect here? The constraints are basically the system dynamics, because from this system dynamics we will be able to get X, and from the output equation we will be able to get the prediction or the predicted output, right? So if you think of Kalman filter now, this model is important for doing your prediction step, right? And this fitting part or minimization term in the optimization problem corresponds to your measurement update, right? So this makes sense? Okay. And the nice thing about MHE, if you already know the control margins for your control input and the state margins for your estimated state, you can put these as constraints. So say, for example, we have a robot that is inside this room and we're doing state estimation on it. We know that the robot is inside this room. So if the state estimator would like to give me like different values for the state estimate, we will ignore the ones that are outside the room, right? And this can be translated as adding a constraint on the estimated state. The same for the control actions, right? Looks very similar to to MPC. It's actually the dual problem of MPC. It's like the state, for linear systems, like state feedback and full order observer. What you do the way you calculate K in state feedback or the gain is very similar to the way you calculate L, right? There you use A and B matrices, and in a full order observer use A and C matrices. You even use the same Matlab command to calculate the gain K and the observer gain L, right? Okay, so what are the advantages of MHE? First off, that deals with the exact nonlinear system. Like if we compare this to EKF, for example, EKF does linearization at the operating points, both for the system dynamics equation and the output equation, right? But this is something that we don't do with MHE. The second thing is that it relaxes the Markov assumption, right? And Markov assumption means that the current measurement or the current estimate of the state and has all the data, or is only enough to estimate the current state value. I mean, the current state depends only on the previous state and on the applied control action, right? So if you do EKF, if you do KF, you look only, or you update your estimate based only on your most recent estimate, right? That's Markov assumption. So you look at your most recent estimate and you build up on that. But here you're looking at your most recent window of estimates or window of measurements, right? So this is what we mean by a relaxation of Markov assumption, right? It takes inputs and outputs constraints in a natural way, like MPC. Yeah, all right, so let's go back to our implementation example. That's our a mobile robot that we wanted to build all the blocks here. So we're done already with MPC, we're done with the controller, and we're now thinking of finalizing or doing MHE, right, to give us the estimate for the state vector x, y, and theta, right? But we did not talk about the sensor yet. So let's now talk about that sensor. So before talking about the sensor, I just want to give you a hint about the disturbed motion model. Now we're doing a state estimation, so we are assuming that the motion model is disturbed. It's not an exact model, right? It's a disturbed model, right? So disturbed model means that whatever control action you send to the robot, V and omega, so I replace them by V bar and omega bar, and V bar and omega bar are the nominal values your controller calculated, and we will add some Gaussian noise or white noise to them with zero means and standard deviations of sigma V and sigma omega, right? So the way this disturbed motion model work is that we, after calculating the nominal control actions, we add disturbance to them, some white noise to them, right? Okay, sounds good. And then the sensor we're going to use is going to be a beacon, and this beacon is fixed at the origin, right? And it measures the range and the bearing of that robot with respect to the origin, right? So it measures pretty much for me this range, this Euclidean distance here, and this angle that this range does with the x-axis. Okay, so but in equations, this is my measurement. This is my sensor. This is what my sensor measures, right? It measures the range and the bearing. The range is basically square root of, or is basically the Euclidean distance. And this angle is arctan y over x. Okay? Right, again our sensor is disturbed or is noisy, right? So when we simulate that sensor, we add also some white noise or Gaussian noise, mu r and mu alpha. And these mu r and mu alpha are Gaussian noise with zero mean and standard deviation sigma r and sigma alpha, right? It's very important that these points are clear to you. So if you have any question, just let me know. Okay. All right. The first question that could come to your mind when designing a state observer is, would this system be observable under this sensor? And observability test, you did already observability test for linear systems. You calculate the observability matrix from the A and C matrices, right? And you make sure that this matrix is full rank, and then the system is observable, right? For the nonlinear systems, things are a little bit different. I'm not going to do observability analysis here, but I will tell you the condition under which this robot is observable. It turns out that the condition under which this robot is observable is when its linear speed is non-zero. So think that this robot is turning in place, right? So the range will be fixed and the bearing will be fixed. So you can estimate x and y, but you won't be able to estimate theta, right? So to estimate theta, you have to interpolate between two different positions to get the orientation, right? So turns out that this observability condition actually makes sense, right? Okay. So again, this is our optimization problem for MHE. What we did not talk about are the weighting matrices for the control and for the measurement. If the noise you have in your disturbed model and in your measurement model are Gaussian, finding these matrices is pretty easy. It turns out that these matrices are, like W is basically the inverse of this matrix, which have the standard deviations for the control V and the control omega, right? So think about it. If the standard deviation for the first control action is large, so this means that the error in the first control action is large, and its penalization is the inverse of that, so the penalization is going to be low. So it's not as effective in my cost function. So when you reduce the weight of something in your cost function, it's not going to affect much your cost function, right? And vice versa. If you increase its weight, it will be dominating the minimum of your cost function, right? Because whenever you manipulate it, this value in the cost function, and it's already multiplied by a large number, so the overall cost function will change greatly for any little change, because it's already weighted with a high number. So any little change would be multiplied by a high number, right? So this will affect your cost function, right? Okay, and if the sensor, for example, for measuring the angular speed is very accurate, which means that sigma is very, very slow, is very, very small, right? And you inverse that, so this means that the weight for this term in the optimization problem is going to be high, right? This makes sense because we would like to give weight to the measurements that are more certain, right? And give less weight to the measurements that are more uncertain, right? The same thing for the matrix V, the weight matrix for this summation here, or for this norm, right? So again, it's the inverse of this diagonal matrix, which has sigma r and sigma alpha, the standard deviations for the range and the bearing, right? Okay, sounds good. So before implementing MHE, let's implement MPC on a disturbed model, right? So everything here is very similar to what we did in MPC, except for a little bit of a difference in the shift function. Shift function was the function responsible for applying the control action and preparing the control initialization for the next time step. So this will be the same, but in applying the control action, we will make a little bit of a difference here. So we'll define a covariance matrix for the control action, which is basically a diagonal matrix of the standard deviations squared on the linear speed and the angular speed. So here I'm assuming that I have a standard deviation of 5 millimeters per second in the linear speed, and I have a standard deviation of 2 degrees per second for the angular speed, right? So that's the covariance matrix. So whenever MPC brings a control action for me, since this is a disturbed system, I'm going to add a little bit of a noise or this much of noise to it, and then I apply this control action to my system, right? So this is how I'm showing the effect of having a disturbed motion model. So that's clear, right? So when we do that, we will get this closed loop response. So this is the these are the states x, y, and theta, and these are the control actions. These are the nominal control actions and not the disturbed control actions, right? Because now I don't know what are the disturbed control actions, and I would like to actually estimate them later, right? Okay, so now we did our like closed loop simulation for a disturbed model, and then we will be doing the for our purposes today we will do the state estimation offline, which means that we will synthesize our measurements, and then we will run our MHE to estimate the states and estimate the control inputs. Okay? Do you have any questions so far? Okay, we just simulated a disturbed model. Okay? Okay, sounds good. So let's now synthesize our measurements. Now I know my states, x, y, and theta. So I would like to synthesize my measurements. So we said that we are having this measurement model. We have this sensor. So let's synthesize R and alpha for all these values of x and y and theta, right? So again, we will define, so this was our control covariance matrix. So we will define a measurement covariance matrix. So this is how much error we have in the range measurement, or that's the standard deviation, so 10 centimeters of standard deviation, and 2 degrees in the bearing measurements. 2 degrees of standard deviation in the bearing measurements, right? So these are the errors, or the standard deviation of the errors for my sensor here. Yeah, so now we're synthesizing our measurements, right? So we will basically go for each x, each y, and calculate these two equations. And for each x and each y, we will have a new r and a new alpha. And we will group that in one matrix. We will call it the measurement matrix, right? Okay. So let's look at these r and alpha visualized. So if you know r and alpha, can you figure out x and y? Yeah, x would be r cos alpha and y would be r sin alpha, right? So let's visualize this and compare it with the ground truth data that we have from the closed loop simulation. So the blue lines here are the closed loop ground truth. So we calculated r and alpha from them, and then we added noise to them. So that this means that when we recalculated x and y from the disturbed measurements, we got these x and y's, right? And we know why it's noisy, because we already added these noise, right? From the measurement model, you cannot directly calculate theta or figure out theta, and that's where the state estimator rule comes, right? So we would like to have a state estimator that gives us better estimates for x and y, not just the red ones. So the red ones seems like pretty noisy, right? And to give us also an estimate for the angular orientation theta. So this is what we need MHE for, or a state estimator in general for, right? So let's look at MHE implementation using Casadi. Just keep in mind all the things you learned from implementing MPC. And one thing of them is the multiple shooting implementation of MPC. So just keep multiple shooting in mind, okay? Right, So we are starting this simulation by just showing you the input control, the nominal control actions we sent to the robot, and the measurements we got from R and alpha. So these are all the control actions we applied, the nominal ones. We don't know what disturbance we added for each time step, right? And these are the measurements we got from our sensor. These are the noisy measurements we synthesized for every time step, right? So I will do MHE in one step, and I will take the estimation horizon to be the full simulation time, right? So we will solve this optimization problem only once, right? So we will not apply MHE in a receding horizon fashion, but like for the first implementation, we will apply it only once for the whole simulation time, right? Yeah, that's what's written there. So I'm going to take my prediction, or my estimation horizon length now. Now we're doing estimation or prediction to be the size of my measurements, right? I will add the constraints that I know already for the control inputs. So this stuff is very similar to what we did so far, right? Defining my system equation in this right-hand side, and defining this function, which when I give the when I give it the controls and the states, it gives me the right-hand side of the system kinematics equation. Additionally, here I'm going to define a new equation, a new model, which is my output or the measurement model, right? So I'm going to define two new symbols, R and alpha, right? And I'm going to define also the right-hand side of my measurement equation, where we have a square root of x squared plus y squared and the a tan of y over x. This is my measurement model basically, right? Okay, I'm going to define a new function, the output function. I'm going to call it h. That's very similar to our notation. So h is a function with label x that takes the states and gives me the measurements. So this function is symbolic function, and this function is also a symbolic function. What is the difference between this function and this function? So these are the right-hand side for the kinematics equation. This is the right-hand side for the measurement model equation, right? This is the right-hand side for a differential equation. And this is the right-hand side for an algebraic equation, right? Because later when we use this function f, we have to discretize it using Euler. So we multiply this by delta t and add that to the previous state. Just keep that in mind, okay? But here this is already algebraic equation, so we will use it directly, okay? All right. Sounds good. The decision variables now are again, the control actions and the state trajectory x. We're doing multiple shooting, right? So that's nice. Like this is even nicer when using MHE, right? Because you already would like to estimate the state x and the control actions u, right? And now we're going to define the parameters vector p, which has two rows, NMHE plus 1 columns plus NMHE columns. The first NMHE plus 1 columns in this matrix P will be my measurements of the output. And the second, just NMHE, will be the measurements of the input, the control actions. So you see how many parameters are in this matrix P? Because every time you call MHE, you have to give it the measurements or the window of measurements, right? And you measure two things. You measure the output, R and alpha, and also you measure the control actions V and omega. And we're lucky because we have two outputs and two control inputs. That's why this matrix has two rows, and this was consistent for all my measurements. Okay? Sounds good. Here I'm just defining the weighting matrices V and W, which are the inverse of the square root of the covariance matrices. These are the weighting matrices for MHE, right? And here let's build up this summation now. So the first term in this summation is the difference between the measured output and the predicted output, right? So the measured output will be parameters vector P or matrix P, and the measured and the predicted output is a function of my optimization variable x. And this function is h that we already defined, right? Yeah, so we will go through this for loop. We will pick a state from the big matrix X, which has my states as optimization variables. We will put it through my h function, which is my output model, and get my predicted, that's the predicted output, and we'll find its difference between y tilde, and y tilde is basically the parameters in this parameters matrix P, right? So after this for loop, I will be done with the first NMHE plus 1 parameters in the parameters vector P, or matrix P, right? And I will be done with the first part of the cost function here, or the objective function, right? I'll go ahead and make a second for loop to fill up my objective function with the second summation here. So the second for loop is one step shorter than the first for loop because these two summations are different in size, right? So I'll get, so what are we penalizing here? The difference between the measured control and the estimated control. And the estimated control is my optimization variable, right? So my control is going to be one term from the big U matrix here, and U tilde is going to be what I have in my parameters matrix P. And this will be in the second part of the parameters matrix P. Right, so this makes sense? Get this difference. Oh, get this difference, penalize it quadratically with the weighting matrix W. And here we use the weighting matrix V, right? Okay. One more for loop for the multiple shooting. We made up this part in the cost function, and we made up this part in the cost function, but we did not put the relation between the X and U. And we already know the relation between the X and U. It's the dynamics equation, right? And that's what we do in this for loop, right? So we add the dynamics equation as constraints because we remember we're doing multiple shooting, right? So these constraints will be upper bounded and lower bounded by what? Zeros. That's right. Again, our optimization variables, the same as multiple shooting, X and U. That's nice. Now our NLP problem is going to, I'll call it just MHE, right? We use the same more or less options as we used before. The same class in Casadi NLP solve, right? With the same options and even the same solver, IP opt, okay? So here the first lower bounds and upper bounds are on the constraints, 0 and 0, because that's equality constraints, multiple shooting. Now we will put the lower bounds and upper bounds on the state estimates for X, Y, and theta, because we know that the robot was moving inside this room. So we already know the constraints on the states, right? And again, the constraints on the control actions, right? Okay. And then we will run that. This is the simulation. Like now we will call the MHE solver, right? Remember that we have to initialize the nonlinear programming problem by values for the optimization variables. Remember also that the optimization variables were U0 and X0 here, right? These two matrices. Here the initialization so far is zeros, right? Okay. I can have a better estimate for U0 because I already know the measured U, so I can initialize U by the measured U's. Okay? And since I also know R and alpha, so I can calculate from R and alpha some good estimates for X and Y for the whole prediction horizon. So why don't I use this to have a better initialization for my vector X0 as well, right? So you can see here that I'm initializing only the X and the Y positions in that vector X, which has already 3 columns. So I will leave the third element to be zeros as initialization, right? So now I'm going to define my parameters args.p, parameters argument that we pass to my MHE solver. And here we're putting our measurements for the R and alpha and the measurements for the control actions, like the nominal control actions we applied. Okay? So remember that when we defined the vector P, it had 2 rows, NMHE plus 1 column, and NMHE plus NMHE columns, right? So here we have k equals already 1. So that's from 1 to NMHE plus 1, like the first NMHE plus 1 terms. We will append to them another NMHE terms. Okay? That's the initialization for my optimization variables. Very similar to what we did in MPC. Call your solver, right? And from your solver, extract 2 things. Extract the estimate for the control actions and the estimate for the states, right? And let's now visualize that, right? So here I'm visualizing 3 things. The ground truth, which we got like in blue here, which we got from the closed loop simulation, right? The measurements for X and Y, because we were able to recover them from just knowing R and alpha, the noisy R and alpha. And this is the MHE estimate, the green ones that we got from MHE. So we were able to get a better estimation for X and Y than the red one. And we also were able to get an estimation for the angle theta. Okay? So far so good? Okay. I think at this point, if you have any questions, just let me know. Because what I'm going to do next, instead of estimating for the whole like simulation time, I will simulate in a receding horizon fashion. So we will set a prediction horizon window, and as we move forward, we look backwards only for 6 or 7 time steps. Like it will be a repetition of what we did already, so nothing will be actually really new. Okay?
What is the time cost to calculate it this way? And maybe this is a better question for once we've seen a windowed version, but I'm curious how those two.
Well, compared to the window version, this would take, of course, longer time. But think of this time of optimization or state estimation problems that it's already done offline. So you don't really care about these. Yeah, but when you do, of course, it in an online fashion, like you want to take this output and give it to MPC to get it working, it will definitely matter. So it will have computational time up very, very close to what MPC has. Yeah. So here I remember that for the whole simulation time we have NMHE equals to roughly 26 or 27. Yeah, so compare this to a prediction horizon of 27 or 26. Okay? And if you remember yesterday, when the prediction horizon was already 100, like multiple shooting worked really pretty well for this problem, right? Okay. So now let's do the same thing, but in a receding horizon fashion. All right? Okay, so what will be the difference? So what will be the difference is the value of NMHE. So now NMHE is shorter than the whole simulation time, right? And we will do our estimation in a for loop. It's not one-step estimation. It's multiple steps, and in every step we look backward for a shorter window, right? So again, we get our measurements and put them in args.p, right? And we update this k every time step. So k starts from 1 and goes up to the last possible window in NMHE or in the simulation time, right? So for every new k, we look backwards k plus NMHE times, right? We get this window of measurements for the output and for the control inputs, and we run the same solver, right? We run the same solver here, and we get the solution, the estimate for X and the estimate for U, right? Okay, so if we run this for our problem, so when will we be able to get the first estimate? We have to wait until we have at least this window of measurements, right? So the first estimate we will be able to find will be after, let's say, 5 or 6 depending on the size of your estimation window. Because normally we are interested in the estimate of the most recent state. I know that we estimate a window of states, but we are interested in the most recent one of them, because that one is the one that we will use later as a feedback for our controller. Right? Yeah, so here for two different NMHE values, like when NMHE is just equals to 6, we got a nice prediction for states X and Y. That's one thing. And you will realize that we start here the estimation after the 6, or after the first window of measurement, right? To the end, right? So you'll see that here, as we go to the end, the estimation for the angle is pretty bad. It's a little bit better when we prolong the prediction horizon length, right? Maybe a reason for that is that as we go to the end, as we approach the end, the linear speed approaches 0, and this makes the angular position unobservable. That's why we get this observation here, or estimation. Okay? So any question?
Is there any way we can do to improve the performance at the end of
It's an observability problem, not actually a problem for MHE. Like even an EKF would have the same problem, because we would like our linear speed to be non-zero in order to guarantee a full observability for the state, right? Think of MHE, think of a state estimator in this problem as something that does something like magic. So if you look at your measurement model, it just has X and Y. There's no theta in the measurement model. And this is the magic of observability, right? A state cannot be even measurable. It's not measured. Theta is not even measured, right? But it's observable, right? And by state estimation theory, we managed to estimate it, right? Yeah. So now let's wrap things up. So these are the terminologies. Some of the terminologies we talked about today. Right, today and yesterday. So we talked about terminologies like numerical optimization, NLPs, QPs, LPs, quadratic and linear programming, cost function decision, variables, constraints, equality and inequality, local minimum, global minimum, objective minimization, and objective maximization. These words all ring bell to us, right? MPC, controllability, prediction model, prediction horizon. Just make sure that you are familiar with these terminologies: OCPs, optimal control problems, single shooting, multiple shooting. These, I would say, the most important two concepts in this lecture, and obstacle avoidance. In the state estimation, observability, MHE, and estimation horizon, right? All right. Some remarks about MPC and MHE. Both are optimization-based solutions, right, for control and state estimation. Both can apply in general to nonlinear MIMO systems, multiple input, multiple output systems. And this is what we did in this workshop. Like our robot example had 2 control inputs, 3 states as outputs. That's already a multiple input, multiple output systems. And even for the measurements, we had 2 measurements. That's multiple outputs again. The mathematical formulations for both are similar. Both can be expressed as OCPs, or optimal control problems. We can take physical constraints into consideration, and we can solve them numerically using NLP in Casadi. To convert from OCP to an NLP, we can do a single shooting, which I think you will not do again, and multiple shooting, right? Well, for small size problems, single shooting is still okay, but you already know now multiple shooting, so why not? So the implementation can be fairly straightforward using some packages like Casadi with its external solvers. Yes, what can you do next? The whole code we discussed in this lecture will be given to you, so you can, in general, replace the model by your model, something you are interested in working on, and it should work, right? Generally. There's something called code generation feature in Casadi. So after we have our code programmed already in Matlab, we can do something in Casadi called code generation. This will generate a C code for my routines and can be converted to a mixed function in Matlab that, when called, can solve our optimization problem 4 to 10 times faster than already what we have. So what we already have is quite good. So we can get it even 4 to 10 times faster by this code generation feature, right? Another package that you may also look at, it's from the same research group. It's called Acado Toolkit, right? It's currently not as supported as Casadi, because, but there is a newer version of it that is under development. It's called Acados, and Acados help you actually to develop optimal control problems for embedded system implementation. So that's even something nice. And by the way, Acados is based on Casadi. So now you know something that's lower level already than something that is already there, right? Because I remember when I used Acado before, single shooting and multiple shooting was just an option that I said in the problem formulation, right? So Acado is actually a package that it's worth to look at it, right? And I actually used it in one of my experiments that I'll eventually show you now. Now we can combine MHE and MPC, one for state estimation and the other for control. That would be a very good exercise. You can take these ideas further to distributed model predictive control, right? Where you have, instead of one robot you would like to control, you would have multiple robots. Each one of them is applying MPC and is sharing its predicted trajectory with others so that the others can, in their prediction, avoid the others' predictions, right? So that's how distributed MPC actually work, and I will show you a couple of demos on that, right? So let's look first at a demo on MHE and MPC. I think the best, so make this PC only because I have this on. Yeah, so this is one example, one simulation example where I used MPC and MHE. Just let me pause this a little bit. Okay, so here we actually have what we call a leader robot and some following robots or child robots. And we would like these child robots, which in this case are flying robots, like drones or something. Okay, we would like them to follow circular trajectories with respect to the leader robot frame of reference, right? So as the leader robot moves, they move actually in circles with respect to it. So we do the control using MPC, and what we measure are basically the range and the two bearings, like the horizontal and the vertical bearing, these two bearings, right, to find an estimate for the robot position x, y, z, and theta, or phi. So here we have 4 states, x, y, z, and phi, right? And we have 3 measurements, range and 2 angles.
Are they holonomic or non-holonomic?
Non-holonomic in this case, yeah. These robots were non-holonomic, right? And actually when we applied MPC here, we have centralized MPC. Because here we have 3 robots apparently, right? So we ended up with a system model that has 3 times 3 states, then 9 states, and 6 control inputs. And we coupled, in the constraints part of the problem formulation, we made coupling constraints between each pair of robots so that they don't collide with each other. So that's called a centralized implementation of MPC. You put everything in one optimal control problem, right? So here we're looking at the problem from different perspective. So this is the general 3D perspective. So this is a 3D perspective, but with respect to the leader robot. So you will see always this point fixed so that you can see the child robots with respect to this leader robot. you see here everything from the top. So as the leader robot moves, you see something, you know, fancy happening to the child robots, but they're actually following just circles in with respect to the leader robot, right? So we applied that for the case when the leader robot is moving in a straight line. And in the following slide, sorry, in the following simulation, you will see the leader robot moving in a circle. So here the leader robot is moving in just a straight line. So you get a really complicated trajectory for the whole system, but it's simply circles, right? So this is the second case where the leader robot is moving in a circle, but each of the follower robot is just following a circle in the leader robot frame of reference, and you will see that the robots avoid collision with each other. And we implemented that experimentally, but for only ground robots. So we had our leader robot fixed, and the ground robots were also following circles with respect to the leader robot. And we set the trajectories, these two circles intersecting in space and time, to see what MPC will do in this case.
Can you go back a little bit?
Yeah, sure.
In terms of the obstacle avoidance, so if you take a look at here, just right here.
Yeah.
So the black one is trying to avoid
It,
the
yeah.
blue one.
Yeah, that's
The
right.
blue one is trying to maintain the constant heading angle. So what is the control policy at this time?
At this time, it's from the MPC point of view. So the optimal, or the locally optimal thing to do here was for the black robot to shift or to deviate from its trajectory, and that the blue robot keeps on its trajectory. Because in the end, we would like to minimize a cost function that has the two errors. So what was optimal or locally optimal at this case was this kind of motion.
So it depends on how you define the cost function.
It depends on how I define the cost function, how I define the weights. Also the prediction horizon length, yeah, and where my optimal solution or locally optimal solution is, yeah. By the way, for those of you who know about value iteration algorithm, okay, so it's in robotics something I would say similar to MPC. And it's one of the techniques used in reinforced learning. So think of MPC that you have a cost function, right? And your reward is to have a minimum cost function, like in reinforced learning, for example. So these concepts are very similar. So you can use actually what you learned in MPC to implement controllers using reinforced learning, right? So let's go ahead and look at the experiment. Yeah, that's the setup. I used a motion capture system for getting the robot positions and orientation. And then I imposed errors on them, and I synthesized the measurements because I didn't have a measurement, a sensor that have this measurement model, right? So I was getting everything, getting the ground truth first, and then synthesize the measurement. Very much similar to what we saw in the implementation of MHE, right? So I have a leader robot, two child robots. I would like these two child robots to follow circles with respect to the leader robot. And these two trajectories are intersecting in space and time. So at some point of time, one of the robots will accelerate a little bit and deviates from its trajectory, and the other one will slow down a bit, and then both of them will converge back to their trajectories. So that's again the reason that one of them accelerated and the other one slowed down. That's the control policy that came from MPC. Yeah, it's something that I did not expect, or I did not want to happen, right? Yeah, so here I have 4 robots, and that's distributed MPC. It's not a centralized MPC. And I would like these 4 robots to exchange positions and orientation, right? So in distributed MPC, each robot applies its own MPC, and it shares its predicted trajectory with the other robots. This contribution was just like a modification to distributed MPC, where we project the predictions on a grid, and then instead of sharing the exact prediction, we share the grid, right? And it worked pretty much the same, similar to the regular distributed MPC, right? So in distributed MPC, each robot applies MPC on its own, and it shares the predicted trajectory with others. So think of that as a dynamic obstacle for others. So you remember the part where we talked about the obstacle avoidance? We assume that the obstacle position is constant for the all prediction steps, right? Here the obstacle position is basically time varying, right? So this was the experiment. We did 4 experiments where the robot, in the first one, just exchanged positions. Now they are exchanging position and orientation, right? So you will see them avoiding each other and converging to their references as well, right? Yeah, I mean the other cases are pretty much similar. Two more slides to go. So we already talked about what to do next. So have a look at Acado, Acados, and of course you have material about Casadi. Yeah, so in this slide in these 2 last slides I put all my publications I have on MPC and MHE, and I divided them with so what is like the work on stability aspect of MPC. That's something I did not go through in this lecture, but I have some work done on it, so you can check it up. And I have also some work on multi-robot control. Actually, these 2 videos that you saw, these are the papers. And work on MHE, and also work on single robot control. Just implementation. These are just implementation papers. Yeah, so that's it again for me today, and thank you very much. So if you have any question, you can drop by or send me a message. Yeah, thank you. Yeah, I'll send out an email with all the details, all the codes, the slides, everything. Yeah.
Can you explain a little bit in detail your experimental environment, for example, in ROS?
In what? In ROS?
Yeah. Did you use ROS?
For these experiments, no. I was using the because we use this on Pioneer 380 robots. So these are commercial or research platforms, right? So, and they come with their simulation packages, yeah. So I was doing the simulation first using their simulation packages, and then I applied this on the
C coding.
A little bit of C coding. Yeah, in one of these papers, I actually developed the MPC using C++. But it turned out later that I can use the Matlab implementation and link it via a window socket with the C++ routines that can then send the control actions to the robot through a wireless connection.
Okay.
So actually, a window socket is something very similar that what ROS does, because all the nodes of ROS communicate locally via IP, TCP communication. So I just did that between Matlab and a C++ routine, right? And that worked fine with me as well, or for me as well. One last thing I didn't mention about Casadi, maybe that Casadi you can implement it in Python, so it supports Python or supported by Python, and also C++. But it's the parts that are the 2 programming languages that are well documented are Python and Matlab. Right? Yeah. Yeah. So any other question?
I have a question about the time cost. And what if you have the kind of LiDAR-based sensor, which will give kind of increasing number of the information based
Mhm.
on the angle. So in this example, we just use the a beacon, which is just give the relative distance and the angle too. But in LiDAR sensor,
Mhm.
we have a bunch of this set. So
You can, it depends on the feature that you would like to capture from the LiDAR.
Mhm.
So your LiDAR gives you, for example, 180 measurements. So maybe you can put like a tower on your robot that has a shape of a circle, and you fit the LiDAR data that looks like a circle, and this will be your measurement. Because you will get your LiDAR data, right?
Yeah.
So if one part of it fits a circle, so this will be your robot position as seen from, or your landmark position as seen from the LiDAR.
So basically, we are assuming that we cluster the occupancy grid-based data into kind of agent level, such as landmark or
Yes.
obstacles.
Yeah, that's right. That's right. Of course, there are also some other problems like the correspondence. Like, how did the leader robot know that this is robot 1 and this is robot 2? There's a correspondence problem. But I did not take this into account. I mean, I assume that this one is solved for me, right?
Yeah, and additional question lies in the same kind of direction. We are operating our robot in bus-based one, and we are having kind of occupancy grid map.
Yes.
And in the map, the obstacles such as wall is expressed by kind of set of the dots.
Yes, that's right.
That means in order to apply this kind of obstacle avoidance strategy, the one way is doing that is we can increase
Fit
the number
circles.
of.
You can do that, yeah.
Then how can we do that in other way?
I mean, the one that I think of is that you can like fit larger circles to your obstacles, right? And you will try to minimize the number of circles as much as you can. So you just fit circles to where your obstacles are and simply use the obstacle avoidance technique we talked about here. That's one thing. Yeah.
Is there any good way to make the constraint, geometrical constraint, such as kind of upper bound is 2 and minus 2, but we have kind of corridor?
Yeah, yeah, yeah.
There's like geometry, and is there any?
There is. I mean, in this case, I would say it's better to use a path planner first, and then give this path to MPC to just.
Assuming we are having the open space, is that
Or even a closed space. I mean, if you use A star or like A star path planner, for example, like right, so it will give you a trajectory like the obstacle-free trajectory. So this obstacle-free trajectory can be given now to MPC as a reference to follow. So you can do the control on 2 steps: path planning, then path following. So path planning, you can use any of the standard techniques for path planning. I mean, if the obstacles or if the geometry is really difficult to formulate in MPC, if you can, that's nice because MPC does the planning and gives you the control action, so it does the 2 things. But if you can't, or if it's mathematically difficult to formulate, so then you can use independent path planning and then do path following using MPC.
in such a strategy, we are assuming the MPC is being operated in an open space.
Yes, that's right. That's right. Yeah, that's right. Yeah. And in this case, you can actually put constraints on the sides of the path that you want your robot to be around this path, like within a certain margin or tolerance. Yeah.
So can't we just use the map in order to change our constraints? So we had here a box constraint.
Yeah, yeah. This is what he was talking about. So
Yeah,
box
yeah.
constraint is easy.
Yeah.
You just put an upper bound and lower bound. But if you have, some irregular shaped, obstacle, and it takes a good part of the map. So, and if you approximate it by a circle, you will lose other parts in the map that are already free.
No, I mean the question. So it is possible for MPC to have constraints that are changing.
Yeah, definitely. Yeah,
Yeah, this is
definitely.
just-
Yeah, definitely. Yeah, definitely. Yeah, but then timing is important.
Timing of the change.
Yeah.
Yeah.
Yeah, because when you do prediction, you do this at predicted time steps, right? So if you want to avoid obstacles that are moving, so you should know where in the prediction or the predictions of their future motion. Okay.
Very much.
Okay.
For the MPC, so MPC has been developed very actively recently, and then I think my feeling is almost reached the stage that it became very popular. So like PID control.
Yeah.
Several decades ago. So it's if I attend PhD comprehensive exam, maybe 8 out of 10.
We'll talk about MPC.
They use MPC in one way or other. So it's very common and it's very accessible these days, and especially the vehicle control area. Pretty much everybody, I think it's almost default controller they use. So in other sense, it's very difficult to make any theoretical contribution. I think it's significant that he was able to make some contribution in the stability. So maybe some stability side or some improving the algorithm side, something like that. But it's mostly application. So I think it's probably useful to get familiar with this implementation using these tools. Try a couple of systems that you work with and get some feeling, and then you will have a good idea of how you can make good use of this. It will be very useful if you have some very good understanding and feel for this MPC technique, how we use in practice. So, yeah, very nice mini lecture.
Yeah, thank you.
Very nice.
Yeah, thank you very much. Thank you.
Very good.
Thank you.